We're okay with the tables kinds of things. We were okay with working in the tables yesterday? Yeah, that wasn't so bad? Okay. I will ask a table question. Always, not always. AP I do. And the normals I don't. And I should probably. Okay, so suppose h of x is f of x times g, or f of g x and prime is 0. So find g 0. Oh, that's cool. Oh, I was like, this is going to be a traditional. No, it's not. Cool. H prime of x equals f prime of g of x times g prime of x. So what do we know? We know g of, so we want to find h, and h prime of 0 is 4. H prime of 0 is f prime of g of 0 and g prime of 0. Okay, tell me something we can do with this. G of 0 is 1. So you take out g of 0 and you put a 1 right there. Good. What else do you know? You know you don't. F prime of 1 is 3, so you could put a 3 underneath. Okay, that's 3. What else do you know? So what's g prime of 0? 4/3. Cool. I know you're so traditionally like, yeah, no, just multiply those two numbers. No, I won't. Yeah, exactly. No, I don't think I could ask you g of x. That would, I could ask you what h prime of, or f prime of 1 is. Because I can't ask you what g is because I don't know enough information. Leibniz rule for chain rule. So I asked you guys to look at this as kind of like a chemistry unit conversion. If I want to know how y changes with respect to x, that's what this is saying, how y changes with respect to x. And x is, and I had some really bad formulas yesterday, but I was trying to think about, I think this is a better way of explaining it. If I have a volume of a detonation of an explosive or a balloon, I put some gas in a balloon and I blow it up with hydrogen gas, and then I put a fuse in it and I light it. Well, everybody's seen that in their science class, right? What hydrogen looks like when you light it, it explodes, right? And it actually explodes almost in a spherical shape. Okay, so if I want to talk about how fast the volume of the fire is expanding, I need to talk about how fast the radius is changing. Would you agree to that? And the radius of the explosion will depend on time, the length of time from the explosion. Yes? And I always tend to really overdo it, and I talk about a nuclear explosion, some sort of nuclear device going off, because we actually know how fast, the Americans have done a lot of research on this, how fast that mushroom cloud will expand. And it basically expands, and the shock wave expands in the shape of a circle. So we can talk about the volume of the shock wave, and we can also talk about how fast things are moving. So it's kind of a really awful example, but people can visualize it. So the volume of the sphere depends on its radius, and then the radius of the sphere depends on time. So I was just going to make something up here about t squared. So if I want to know how fast the volume changes with respect to time, I need to know two things. So if I want to know how fast the volume is changing with respect to time, which is why this notation is very common and prevalent in science now. It's because the formula tells you what you're interested in. How fast is the volume changing with respect to time? I need to know how fast the volume is changing with respect to the radius. And then I need to know how fast the radius is changing with respect to time. But all it is the chain rule. Formulas within formulas. Yeah, well, okay, so if I call this f of x, or f of u, and u is x squared, is exactly the same. The benefit with the Newton's notation is everybody not everybody understands it, but it's very mechanistic and everybody understands the process you do. The derivative of the outside, leave the inside of the loan, times the derivative of the inside. With Leibniz's notation, that might not look the same, but it gives you some real context. The formula has real meaning. At least it does to me, because I can look at this box and say, okay, I want to know how fast the volume is changing with respect to the radius, and then I want to know how fast the radius is changing with respect to time. Okay? Kind of get what I'm saying here? Maybe a little bit? No? Whatever? Whatevs? Okay, so given y equals u squared and u equals 5x cubed plus 2x, find dy dt. Okay, this means find how fast the y values are changing with respect to the variable u when u is 9. So all I'm asking you to do is it's kind of dorky, but I don't even see this right now. I don't see you. Don't do this to your page. I don't see you right now. All I want you to do is to take the derivative of that. 2u. Everybody put 9 in for u, please. Yeah? B. B is saying, I want to know how fast u is changing with respect to x. I don't see this now. Just take the derivative of this. (15x squared plus 2). Put 4 in for x. 15 times 16 plus 2. 256 minus 240, 242. You guys know what I did, right? 16 times 16 is 256. Minus 116 is the same as 15 times 16. Because it's slower. It's 240 plus 2 more is 242. 15 times 15 is 225 plus another 15 is, I don't know, because I like my 16 squared better than my 15 squared. I don't know. Spencer, don't make me feel stupid. I don't know. You're right, I should have used that strategy. Okay, so dy dx when x is 1. So what I need to know here is dy, just like Mr. F, y depends on you. dy du times du dx. What's dy du? No, don't put the number in. Just 2u. What's du dx? Okay, it says when x is 1. So we need to know, okay, x is 1. We need to know what u is. When x is 1, u is 5 cubed plus, good, you're doing it, 5 times 1 cubed plus 2 times 1. Yeah, but let me write it down. 7. So wherever I see a u, I'm going to put in 7. Whenever I see an x, I'm going to put in a 1. Times 17. Yucky. I think I have to do this in old school. 4 times 7 is 28. Shh. 68. Don't make me feel dumb. Yeah? Is that all right? Is that a little bit better than yesterday? I'm walking you through it. Yeah, do this, then this. Could I walk you through it? Yeah, a little bit. What? You like do this, then this. Well, the neat. Yeah. The neat thing about and not that I'm asking you to write this down, but the neat thing about the chain rule in Leibniz's form, you can have you can run just about you can have a whole bunch of chains run together. If you have formulas within formulas within formulas within formulas, if you want to know how fast something is changing based on that very last one, you just got to work your way all the way over until you've got all the formulas there and which one do you need. And that's the nice thing about this one. With Leibniz's rule, it's not as pretty when you do formulas within formulas. Okay? Whatever, Mr. Whatever. Whatevs. Okay, flip the page, kids.